Okay, well, I'd like to thank the organisers very much. Firstly, for organising this conference in the first place and for inviting me to talk at it. It's something quite personal for me because I knew Jan Nekovár for over 30 years, and we were very good friends and had quite a long mathematical collaboration. I just thought at the beginning I would just show you just one photograph of Jan in one of his lighter moments, which is not always seen. This is from Overallfach in 1994. Obviously, this is having a good time in the days when Jan could still drink Alpiersbacher.
Was the shirt drawn by his sister?
Sorry?
The shirt is done by his sister.
The shirt is indeed done by his sister, and I think I even have the photo, the picture from which it was made. Do I have anything? Yes, I do have one other thing. I'm not sure what it is. Yeah, maybe I will show this in a moment here. Okay, and yeah, so I think I need the glasses after all, otherwise I can't see my notes. Yeah, so Jan would have been 60 this year. I think if anybody who's familiar with his work, and this will certainly be made clear after Olivier's talk on Thursday, we'll realize that he was at we'll understand the trajectory of his work and that he was really at the height of his mathematical powers, and that there was much more that he would have done in the years to come, and so we will miss him for all these reasons. So what I'm going to talk about is the collaboration that, a small part in fact of the collaboration that Jan and I began in around 2007 and continued up until his death, and there are still things which are going to appear. There's a 125-page paper which is should be out in a week or two. And we came at this from two different directions. But first of all, maybe I just say about, Jan was somebody who tended to think of mathematics as something that you did by yourself rather than in collaboration. So I feel rather privileged to have had such an extensive time working with him.
Does that mean collaboration, you don't sing by yourself?
Sorry?
Does that mean collaboration means you don't sing by yourself?
No. And I should say that maybe sometimes I felt that this collaboration was more like the relation between a PhD student and their advisor. In this case, I should make it clear that Jan was the advisor. But we would sit around and spend a lot of time doing what he would call armchair mathematics. But we also had times when we would just sit around and
what did you say? Which kind of mathematics?
Armchair mathematics. Yes, I leave you to guess what the definition of that is.
He attributed this terminology to you, Tony.
Sorry? Attributed this terminology to me. That's very kind. Okay. Yes. So anyway, so perhaps to turn to maybe I'll just say one more thing, actually, going back a bit about Jan's okay, no, I think I will let me come back to that later. And I think you can turn off the slides now. Okay, yeah. So we came from two different directions. So I was thinking for a long time about how to generalize classical modular constructions to higher dimensional Shimura varieties. So, for example, what is the analog of a modular unit for a totally real field. We have all these beautiful formulae for classical modular forms, these explicit formulae, infinite products, these wonderful theta function identities, and so on. And very few of them seem to generalize to high dimensional situations. The formulae have wonderful applications in number theory, and so I spent a long time thinking about what these generalizations ought to be. Jan was also thinking from a slightly different point of view about Euler systems and wanted to construct more Euler systems. And when we sort of put these two things together, we came up with these, what we call the Plectic conjectures. And I want to explain what they are and actually explain where they came from, which is basically a summary of a conversation, of a discussion Jan and I had back in 2007. So let's start with, so thankfully yesterday we had a very nice introduction to Euler system by David. And so let me start off by just saying something about sort of one possible model here of a geometrically, an Euler system of geometric origin, which is the Kato Euler system. So we take E over Q to be an elliptic curve. And if we take T to be its, say, p-adic Tate module. So an Euler system we want to find cohomology classes inside this cohomology group. And the way that you do that, or the way Kato did it, is you take Y, which is some modular curve, but you want your modular curve to have constant fields, this cyclotomic field. So you take full level structure at n and then some other level structure. This gives you a curve with Q zeta n inside the field of constants, and you assume that we have some modular parameterization as well, so that the conductor of E divides the level of Y. And then you look at the L-adic cohomology of this, let's say with coefficients in, I don't know, what are we doing? There is P here, in ZP1. Except we're going to look at ZB2 first. So inside here there's a way of constructing elements, namely we just take moduli units. So this is just Bailenson construction. And we just take the Chern class into H1, and the cut product gives us this map here. So this gives you a family of elements here. And now you then use the this parameterization to get a map into H1, and the also by the Hochschild spectral sequence to H1 of Q zeta n. And so that will be with coefficients in the H1 with a 2 twist, which is the same as T twisted by 1. So we get the elements in here. This is almost the same. We have this twist here, but since you can take all possible n, you can basically untwist this by twisting. You get elements here, and that's the construction of the Kato Euler system. Now, Jan wanted to define Euler systems so we now take an elliptic curve over a totally real field. So let's say we have, say, degree R totally real. And we take E over F. Now, what should be an Euler system? So Perrin-Riou tells us where we should look for an Euler system. Or for T, let's say, should live now not in these groups, but in the rth exterior power of, let's say, K F zeta n T. So this is what's called a higher rank Euler system. The point is that these Euler systems are used to annihilate elements of Selman groups, and basically you need R of them. So you need an element of this. Okay, so let's just look at the case when n equals 1, because it'll be clear that this one. So you want at least to be able to write down some elements of H1 of F with coefficients in T. So how are you going to do that? So this is the calculation. So let's write gamma F for the Galois group of Q bar over F. So then the wedge R, this is a sort of the cohomology group we actually are looking at. So by the Kunith formula, this is essentially, we're going to ignore some torsion here, it's essentially just the HR of the product, our full product of gamma F with here, and then we have to take the invariance on the symmetric group, SR it is, okay. So this is, we ignore torsion, or some torsion. Okay, and this is just, again, ignoring some torsion, it's just the HR of the semi-direct product of the R-fold product of gamma F with the symmetric group. So this is a symmetric group. Okay, so instead of looking at elements of some wedge, which are clearly going to be rather hard to do, we've got some other cohomology group involving this group here. And this is just the tensor induction. Well, I'll have to explain that in a moment, of T. Okay, and David explained in his talk already that this tensor induction occurs in the cohomology of a suitable Shimura variety. So if we assume now that E on F is modular, so it's associated to some automorphic form on GL2F, then let's call it the tensor induction from gamma F to gamma Q of the, let's say, the QP cohomology of E occurs, okay, so this is up to semi-simplification, in the middle cohomology of S. So where S here is some Helmholtz-Blumenthal variety. Over Q. Sorry? Well, I've got an H upper one here, haven't I? Yeah, here I would nature of 1. I put that. Yes, if I were to put T here, I should actually have to put a twist by R. Yes. Okay, so we've gone from a problem of constructing elements of this wedge, where we have F rather than Q, to something which is actually over Q, apart from this funny group here. And people have thought about this, how can you use these Shimura varieties? So this is associated to F, but that reminds me I should switch off my phone as well. Hey, I can figure out how to do that. What is it? Do not disturb. I think that's right. Yes. Right. So, yeah. So, if we look now at the picture of Kato's Euler system, so we were looking at the H1 with coefficients in T, and we use the Hochschild spectral sequence to relate that to the H2 of the modular curve and construct elements inside there. So that sort of suggests that maybe, so this is inside the cohomology, again up to semi-simplification anyway, but we'll come back to that in a moment. So is there then some map? So this is inside the HR. I'll just write the HR of S here over Q bar. Yeah, but and indeed with this Tate twist. Right? So now the question is there some sort of, I don't know, funny cohomology of S, which will have coefficients in, I don't know, ZPR, together with a spectral sequence relating these two things. And then we would need to have some elements inside here. So we'd have to construct some geometric elements. Okay, well, this does seem a bit far-fetched, but so there are two questions here. So that's question 2. But question 1 is even, is there action of this group on this cohomology which would fit into this picture? Does this group act on the cohomology, the geometric cohomology of this Shimura variety? Now, there's no clock here, is there? Somewhere? Ah, yes, okay. Okay. So let me just say something about this group here. So there are two other descriptions of this semi-direct product. So the first one, and this occurs in Jan's paper on hidden symmetries, is that this, so these are a bit more canonical. If you take the algebra F tends to Q bar, then the group of F automorphisms of this, as an F algebra, is isomorphic to this semi-direct product after you choose some coset representatives and so on. And here's another description of this, is if we take the group gamma Q, and now we regard this as, consider the action of gamma F by right multiplication. So it's a right gamma delta set. So if you consider the automorphisms of this as a right gamma delta set, well, it's just a union of R primitive orbits. So you see rather easily that's just a... Sorry? Delta is F. Well, I said what gamma F is. It's just the absolute gamma group. Okay, so these things are rather easy to check. And you also see that, of course, inside both of these groups, you can see immediately gamma Q embedded in them, just as automorphisms of the second factor. And here it's just given by left translation. Every left translation is an automorphism of gamma Q, which commutes with right multiplication by, certainly by gamma F, indeed by gamma Q itself.
You can see gamma Q already embedded in the weak product.
You can as well. Yeah. Yes. But to do that, you need to make some choices. Yeah. Okay, but these two descriptions are both completely canonical. I mean, they don't depend on any choice of coset representatives, or so on. Okay, now, so what about this? Okay, so now we have this tensor induction, and of course, tensor induction is, so what do we say about the tensor induction? So we have T, and we have our gamma F, okay, that's I'm going to call delta, acting on T. That's inside, I'll just call it gamma for now, gamma Q. So what is this tensor induction? So what is this tensor induction? Well, how do you define induction? You take gamma cross T, and you take the first projection down to gamma, and then we take the quotient by the action of delta on the right, here, and then the induction, so let's call this pi, the induction is just a set of sections of this bundle. That's the usual definition of induction, which you can also think of just as being this is find index, it's just the direct sum of the fibers of this map. The tensor induction is just the tensor product of the fibers of the map. It's just the tensor product over S in here of pi inverse S. Okay, that's completely canonical, doesn't depend on any choices. And anything that acts on this diagram will therefore act on this thing here. Multiplication on the left by gamma acts on this diagram. So that gives the action of gamma on the tensor induction, which is just the classical tensor induction, written in a completely coordinate-free way. But also any automorphism of gamma, which commutes with the right multiplication by delta, will act on this. So this group here acts in a canonical way on the tensor induction, and the tensor induction, the gamma Q, is just the restriction of that to the subgroup. Okay, so this is just some triviality. Okay, so now I'm just going to tell you what this Plectic conjecture is. So the Plectic conjecture, in the simplest case, so it just says that there exists a functorial Well, I'm going to, this is not right. I don't mean a functorial complex. I mean a functorial object in the appropriate derived category. It's called an R gamma plectic S. Okay, well, we did this for QP coefficients. You could do Z. There's no reason why one shouldn't ask the same question for ZP coefficients. So this is a complex of modules for this group. Let's give this a name. Any of these incarnations of it, we'll call it the Plectic Galois group of F. Okay, so there exists a functorial complex, which is sort of refining the usual. Maybe I should put a Q bar here. A complex of. Okay, and then we can define then the plectic cohomology of S, and there might be some twist here. Oh, well, there might be coefficients, but this is the simplest case. It's just we take the cohomology, the group cohomology, well, continuous group cohomology of this with coefficients in this complex. Okay, and if such a thing exists, so this is sort of to be thought of as a refinement of just the usual étale cohomology of S over Q. And if this holds, then we do indeed get, so this funny is now plectic. It took us some time to change from one word to the other, but it's now plectic. We give it there will be a spectral sequence, and in our paper called Introduction to Plectic Cohomology, we wrote out lots of hypothetical constructions that you could do if you had this conjecture, basically along the lines of what I was hinting at in these top boards here.
Tony, Tomoyuki is asking what functorial means.
Functorial. So, for example, you have Hecker operators, and we want them to act. So, I mean, I haven't said precisely what S is. There's some level involved. There are maps between them, and so we have Hecker operators, and particularly we want those. Yeah, I mean, there's a much. I'll say in a moment. There's a more general conjecture for more general Shimura varieties, which were already I hinted at in the abstract. Okay, so that's the answer, or not answer, to question 2. But so there's still question 1, which I should say something about. Is there any, is there any hope of this thing working? So maybe I should just move. Let's see what I want to do. Try and reverse. I'm sorry?
In question 2, you wrote geometric elements.
Ah, okay. Well, okay. So there, this I am not going to go into, but if you had this formalism, then many of the constructions that you do for modular curves would carry over into this context. So in particular, one would get, instead of here having elements of H2 with 2, one would have H2R, 2R, and one could do things with them. I don't have time to explain all these things you can do with it, but we wrote out in our paper basically what the arithmetic consequences of this would be.
And they also come from units, from parent units.
Okay, no, I have that. That I'm going to say a little bit more about at the end. Okay. Yeah, they're not units because there are no modular units. You have to use something else. Okay.
Can I ask a very simple question? And maybe you already said, but I didn't catch it. Where does the word plectic come from?
It comes from spending a little while talking to some Greek people and consulting a classical dictionary. Okay, we had to include in our paper Liddell and Scott, which is a standard Greek to English lexicon in the bibliography.
And what is the meaning of plectic?
No, it means folded or wreathed. So because we have this wreathed product here, that's the...
The same plectic as in symplectic?
Of course, yes. I mean...
Can I say something about that?
Yes.
Who has the question?
Shimura, that's it.
So if you read the tragedy Oedipus Rex,
Mm-hmm.
you know, so in the end Oedipus finds his wife, who is also his mother, and she hanged herself, right? So if you read that in original Greek, you will see where Plecton comes from.
First thing when I get back.
So we have to hang ourselves to understand the theory.
Well, the moral of the story is that he unplects, so he de-reaves the person. So maybe that's also the moral of that story.
But he still died, right?
Yeah, too late.
Okay, well, since we have no idea how to prove this conjecture, it would be perhaps a good idea to say why it is reasonable, or some sort of evidence. So the first thing is that it's true in dimension 0 in some sense. So if you replace this by Shimura varieties of dimension 0, then it holds. And that comes down to some statement about complex multiplication theory. So let me formulate it more precisely in the way that Jan did. So let's look at S. Q bar. So inside here, you have special points. Well, S itself parameterizes, so S is a coarse moduli scheme for abelian varieties plus endomorphisms by, let's say, OF, and then we got unleveled structure. Okay, I'm leaving out polarizations. So inside here we have special points, and these just correspond to abelian varieties with Cm by some k over whose real subfield is F from Cm field. And so then Jan proved this beautiful theorem. So the action of gamma q on SQ bar, well, let's say the special points, so we'll call it SQ bar special, extends And this is given by the Tate-Deligne formula. So there's an explicit formula in complex multiplication theory. This proof relies on Deligne's theory of absolute Hodge cycles, which gives a precise description, precise sort of non-abelian description, because of the action of the Galois group on the special points, and this extends to an action of this Plectic group, also given by some explicit formula, rather more complicated. Okay, so that's the theorem. That was, well, the paper was written in 2006, but it didn't appear until 2009. So that's one piece of evidence. And then here's another theorem, which is actually more than one theorem, but I'll state it like this, is there exists an action, possibly several, of the Plectic group on I'm using P out today. So on the cohomology of the Shimura variety, extending the action of gamma Q. Okay, and this is a combination of various things. So first of all, there's the hard bit, the really hard bit, is the cuspidal part. So that's the combination of the two things. That's first of all the description by Rylinsky and Labesse of the cohomology, the cuspidal cohomology, up to semi-simplification. Okay, and then you've got that.
So can you hear S is really just Hilbert-Blumenthal or more generally?
The S is Hilbert-Blumenthal, and I'll be a bit more precise in a moment. But yes, S is Hilbert. Yeah, S is here. So far, S is Hilbert-Blumenthal. That's Rylinsky-Labesse, and then there's also this Nekovár semi-simplicity theorem, which is really a really hard result. So knowing that it's semi-simple, then we know how this is actually occurs. This is true on the nose, and that gives, because it's a tensor induction, an action there. And then there's a much easier part, which is to consider the non-cuspidal. And so this I did with a student, Davidescu. Here the problem is that, and there was earlier by, this builds on work by Harder and Kasper. So the problem is that we're looking at a Hilbert modular variety, so there is some part coming from the cohomology infinity. There's a non-trivial wave filtration. The wave filtration is not split. That's something that Harder discovered and was analyzed by Kasper in his thesis in the case of a Hilbert modular surface. So we have to actually exactly write down what the extension classes are, show that they extend to elements, to extensions of the in the cohomology of this Plectic group. But that's relatively simple compared with a semi-simplicity theorem.
And what is the reference to this theorem?
Which one? There, here, and here.
Year or something?
Oh, year. Semi-simplicity was 2019?
I think. The publication date, I think it's 2019.
Yeah.
No, I mean, this theorem is written where? In this paper of 2019? Or?
I think you'll find, I think we wrote it in here. I think we wrote it down in here, yes. I mean, but I mean, it's a composite of two theorems, really.
So there's possibly several action. Is it, do you expect there to be canonical one, or is this?
Oh, we want to go, yeah, I mean, this should be this complex should be functorial, so yes. But the problem is that the tensor induction needn't be irreducible. So you could have various possible extensions. I mean, as a representation of a gamma Q, it might not be irreducible. Okay, so I think I have, what, 15 minutes left?
Tony, is there also evidence in the function field case? Say?
Okay, yeah, there is. I'm not going to say that, but I mean, it was the very beginning of the Jan's Hidden Symmetries paper. He says, well, you know, there's a sort of, you know, if you believe in the field with one element, there's an explanation for why this is true. Because you've got that sort of why this might be true, because in the function field case, it was clear at that stage that this ought to work, and people have worked out some things in the function field case. I think even some people who are in this room. So, yeah. I mean, in the function field case, there are different problems coming from the, you know, the complex geometry, the difficult geometry of the moduli space of Stuka. I mean, if there were some applications in the function field case, that would be really nice. I mean, this is sort of implicit in some way in this sort of okay, well, I won't go into that. I think that would just that's not my area, and it would just detract from. I seem to be running out of time as it is. Okay, so yes, as Vivja said, what is S? So S could, I mean, here S is a Hill modular variety. More generally, one could ask, well, no, we decided we really wanted to put this in a proper framework. I mean, here already in the case of special points, you're really looking at Shimura varieties of dimension 0. So given by some tori. And so the general framework, which, in which we believe that something like this ought to be true, is when you take, so more generally, if S is a Shimura variety Shimura variety is associated to a reductive group G over Q and some symmetric space X associated to G, which is just some consciously class of co-characters, of complex co-characters. And if G is the restriction of scalars from F to Q of H, where H is a reductive F group, then a conjecture should hold for the cohomology of S. But now, because S is defined over some number field, which is the reflex field, which in general is not Q, and so you wouldn't expect the whole of this group here to act. We have to replace the Plectic group by some subgroup, which will just be the stabilizer of, so there's some co-character attached to this Shimura datum. The stabilizer of it in its conjugacy class in the Gower group is the fixed field of that is the reflex field, and So we can do the same thing in the Plectic case. So you can define this thing and say exactly what that is. Okay, now coming back to the classical constructions, modular constructions, things like modular units, the way you actually do this in practice is not just by looking at the modular curve, but you also look at the universal elliptic curve. So these are just related to the universal elliptic curve, let's say E to M, so M is some modular curve. We've got the universal, let's call it E universal. And this is an example, the simplest example of a mixed Shimura variety.
So the gamma F is the mu plectic. What is the relation of this to the one without mu? Is it?
It's a subgroup, and if you take the intersection of this with gamma Q, you get gamma of the reflex field. So this is a subgroup of the gamma plectic.
What would this be for a Shimura curve?
What?
The stabilizer.
Well, if you've got a Shimura variety of type signature T R minus T, in other words, for attached to a quaternion algebra, then the group is gamma F to the T, semi-direct product ST, product gamma R minus T, F, semi-direct product SR minus T, and this thing acts trivially. But it's not clear what this means, because, well, yes?
Just to clarify, T is the number of places where you are matrix algebra or quaternion algebra?
T is the number of split places. So this is the matrix algebra places, yeah.
So what you have written here is what? Is a group that...
See here?
No, in the group that you... What does it... This is a group that acts on
So David's question was, suppose H is the unit group of a quaternion division algebra. Yes? So his question is, so therefore the Shimura variety is a Shimura curve in the case of a one split place, or more generally these varieties that Shimura considers in his papers. And then the question was, what is this group in that case? And the answer is, it's this subgroup of defined index. Basically, the symmetric group is just, you take ST cross S R minus T. Okay. Okay, what was I saying? Yes, we have this. So this is a mixed Shimura variety, which means you take not just a reductive group, you take some connected algebraic linear group, which in this case the group is GL2, semi-direct product, I have to remember to check this, with GA squared. Okay, you see GA squared, I mean the real points of GA squared, together with the complex structure coming from the torus inside here, give you the elliptic curve, the fibers of the elliptic curve. Okay, so there's this theory of mixed Shimura varieties. And now if we do this over F, now we run into a problem. So there's a problem. Okay, so I said somewhere that S was a coarse moduli scheme. It seems to have gone. I erased it, okay. So S is a coarse moduli scheme because if we have our abelian variety has automorphisms, inside the automorphism, you've got some always got some finite index subgroup of the units. No matter what, if you just impose a level structure, you just pass from, you have to look at units congruent to 1 modulo n. But so, because we haven't imposed a polarization, this is just a coarse moduli space. So there's no universal abelian variety, abelian scheme. So there are two ways to solve this problem, and one is good and one is bad. So two possible solutions. Okay, and this was actually one of the key things in formulating the conjecture, was to understand why we should do one and not the other. So one solution is you replace S by S prime, which way you can set it, you add polarizations. And the associated group, G prime, is the subgroup of GL2, the restriction, consisting of things, so the determinant goes to RF on Q GM, of things whose determinant is rational. And actually, this is sometimes what's classically called the Hilbert-Blumenthal variety. This has the advantage, when you add the polarizations, after you have sufficiently high level structure, you have a fine moduli space, so therefore you have a universal abelian variety. So that's one solution. The other possible solution, I think I may as well just use a small board. I seem to be running out of time and therefore we won't be writing that much more, is to use, so that's one possibility. So just work with the stack. In fact, the stack in this case is rather easy to describe, because there exists some abelian scheme which is, in a way I'll not make precise, is almost universal. Let's just say, at least it's got the right fibers. But it's also got delta acting. Delta now is this fine subgroup. Okay, forget about that delta. Yep. And so now you can just, the stack is just you take the quotient of this abelian scheme by delta, that maps down to quotient S mod delta. Delta is acting trivially here. So this is just S cross, let's call it B delta, just the classifying stack of this discrete group delta. Now, what is this thing? Well, it's really horrible. Because, I mean, you just look at a fiber, you've got an abelian variety with endomorphisms by OF. And then you've got this group delta acting on it by multiplication. So the orbit structure is really not very pleasant at all. So this quotient is geometrically extremely horrible. Okay, so it turns out that this is bad. And this is good. And why is this bad? This is bad. Well, one reason this is bad is because this was already clear in the hidden symmetries paper, because Jan first of all considered, well, in that paper the theorem is stated for this group, not for GL2, and this group doesn't act. Only some subgroup of it acts. the problem comes actually it's just an issue of connected components. As essentially this Shimura variety, in the limit, as you pass over level structures, these two Shimura varieties are the same apart from their sets of collected components. But that completely messes things up. So that's one reason why this is. This is good because the Plectic group should act, and it does act, as we saw in the answer to question 1. And another thing is, so what is the cohomology of this thing? So this is just the equivariant, delta equivariant cohomology. Of A. And if you're sort of grown up used to the studying the cohomology of arithmetic groups rather than the cohomology of Shimura varieties, you'll know that if, for example, you take this group here and you look at its associated locally symmetric space in the sense of cohomology arithmetic groups, it's not that is not the Shimura variety. The associated locally symmetric space is a set of points of the Shimura variety product with the units tensored with R mod Z, tensored with this torus, this real torus. Because you don't divide out by the whole center, you just divide out by the Q split center. So you get the units left behind. And this is just a topological realization. Well, I suppose I should take delta here instead of this thing, of the classifying space. And in fact, when we do computations instead of in L-out cohomology, which we can't do, in real cohomology, which we can do, turns out the right object to work on is this thing here, because this has a natural automorphic life of its own, and the formulae are quite natural in that respect. Okay, so it seems I spent rather longer than I intended on this part of the story, and so have not had time to talk at all about the Archimedean picture, apart from this very short remark here. But I do want to say, a closing remark, there is a quite extensive Archimedean picture, and among the papers that Jan and I were in the process of finishing when he died is one about the sort of Plectic analog of the elliptic polylogarithm, and that is going to appear in a couple of weeks, hopefully. And I think my time is up, and that's 2 more minutes. Okay, well, okay, I don't need 2 more minutes. That's fine. Thank you.
You mentioned that there's an extension of the action of gamma q to gamma f plectic on the cohomology of S, but there were possibly several such extensions.
Yes.
In one of your papers, there's a remark that just hints at how one might characterize a unique good extension. Is there a precise formulation of this conjecture, and has it been proved in any cases?
Well, in the case of the Hilbert modular variety, I mean this GL2 Shimura variety, whenever P splits completely, well, you have these partial Frobenius, which are given by taking. So let's just say that. I mean, you know what partial Frobenius are, but for the benefit of other people in the audience, we have some abelian variety over FQ and something. And then if we look inside, we have the kernel of Frobenius, and we can now also intersect that with the kernel of the ideal P. Let's say if P is just the product of some ideals P. And so if we divide out by this, we get this functor. I haven't only done it on FQ points, but this comes from is given by a map on the special fiber, which is called the partial Frobenius. And the product of these partial Frobenii is just the usual Frobenius. Okay, well, just as there's a relation between the usual Frobenius, geometric Frobenius, and the Galois arithmetic Frobenius, which exists in characteristic 0, there should then be a relation between these partial Frobenii and the Frobenii inside the various factors of this plectic gamma group. So inside there we've got R copies of gamma F, and there's a sort of plectic decomposition group, and now you have to replace SR by a product of smaller symmetric groups depending on the splitting of P, and if P splits completely you just get the product of R copies of the decomposition group. And the conjecture should therefore be that, well, then these partial Frobenii ought to correspond to the Frobenii inside this plectic group. Okay, and then you could ask, and this seems rather likely, is that enough to rigidify the situation? I don't know, maybe you know the answer to that.
I know some sort of partial L equals P version of the answer.
Right.
I was wondering about the L not equals P case.
Yeah. Yeah, I mean, we never sort of got around to thinking about whether that would actually characterize. Of course, it might be, I mean, one particular, yes, I mean, that's, no, I think, yeah, that's all I think that's all I can say. Yeah.
I don't know if it's useful, but part of your story reminds me of the multiplicative transfer of Leonard Evans. You must know that.
Well, there's another paper actually that we discovered quite late on by I think a student of Cartier, whose name is Daniel Ferrand. Right, and so he wrote a paper about transfer and about some categorification of transfer. I think he was doing transfer in some topos. But it's based on a paper by Cartier. It's a completely unknown paper by Cartier. It was in Enseignement Mathématique on and it's not in Math Reviews, so nobody will ever find it unless they know it exists. I have no idea why it's not in Math Reviews, but it's not there. Okay, and if I sort of can connect it to the story here, to the top board, you consider slightly more, you're considering the following data. You consider some set omega, so this is supposed to be a transitive, so I'm going to use my gamma and delta again, gamma set, and you have on which delta acts on, well, commuting with it. And you can use this setup, and so this is slightly, here, the situation up there, we had gamma equals omega. So for example, you could take omega to be equal to the isomorphisms between F bar and Q bar. If you are very observant, you would notice that the Oort F algebra F tensor Q bar doesn't depend on any embedding of F in Q bar, whereas the second description of the automorphism of gamma F sets depends on it. Okay, but you could take this, and now you could take the automorphisms of this, which commute with the action of gamma. Maybe I've written it the wrong way around. Left or right is very... Anyway, so there's Cartier, and Cartier defines a transfer in this setting. And so in fact you could forget about transfer, about gamma entirely, and do everything like this. And in fact it turns out that a couple of the formulae that Cartier writes down are actually the same as the formulae that occur in Jan's hidden symmetries paper, although he had no idea about it, and we discovered this paper long after, because it's a hidden paper.
What's the title of the paper?
It's called, well, the paper by, it's something about remarques sur les signatures, is it? Yeah, you'll have trouble finding it on your phone. You know it. Oh, you did?
Google Cartier permutation enseignement.
Yeah, okay.
Is the first step. So what is the title then? Remarque sur la signature d'une permutation.
I'm not sure if that's the same paper.
No, it's not the same?
No.
Oh, okay. Sorry.
Okay. I think I can tell you what the paper is. It's some Ferrand's paper, I think it's in, isn't it in English? I forget. Okay, I can tell you now. The paper by Cartier is called Sur une généralisation du transfert en théorie de groupe. It's 1970, l'enseignement mathématique. And the paper by Ferrand is called A Note on Transfer, and it's never published. But it's archived on the Internet Archive, so it's always going to be available. Well, until the Internet Archive stops existing.
So is Jan's theorem for the Plectic action on the special points of the HBAV, does this already have arithmetic consequences? For example, can you have some theory of elliptic units or string fields that relate to?
Oh, there are no known obvious consequences of that. Just as, I mean, there are no known obvious consequences of the action of the explicit description of the action of the Galois group of Q on the special points. I mean, there's this wonderful formula by Tate, which was proved by Delaine, but very beautiful description of this using this half transfer. And Jan basically wrote down a Plectic version of that. I mean, it's wonderful, but I don't think anybody knows any arithmetic there aren't many arithmetic applications of that theorem per se.
Because in that case, Katz constructed a P-L function by specializing to these special points on HBAV, but I wonder if you get some...
Plectic P-L function. No, yeah, that's definitely something to think about.
Yes, I had a question, a bit following up on what you said about partial Frobenius models. So as we can see still on the middle board, the action of the Plectic group is a machine to transform the cohomology into a one-dimensional exterior power.
Yes.
And so now putting ourselves on over a local, we take a local model of the Shimura varieties, and then we have a description in terms of the local lambdas correspondence. And in that case, we also have some sort of machine to produce one-dimensional thing, which is the Bernstein-Zelinsky derivative. I always wondered if there is some sort of Plectic Bernstein-Zelinsky derivative. And it would account for this partial Frobenius compatibility in some sense, because you go full Langlands, you apply Bernstein-Zelinsky, you get the L factor there, so it would match. But it should match, there is something to match too. No.
Oh, that's a very interesting question. I hope you can answer it.
But I can't.
Okay. David. I can do that one more. Is there a Plectic version of Heegner points?
Oh, that would be an entire talk. Yes and no. I mean, there's an obvious candidate. You take the Shimura variety, again, for this here. You take special points. Okay, so you take that, and so you get some class. Your cohomology, you'll have some a special point, a cohomology class. So there has to be a plectic class with line H2R S with values in, I don't know, plectic ZPR. Okay, now you project and do the same thing as in well, the black was gone, but then we then go to H2R, HR of the plectic group. Well, let's go straight into here, we ended up in here, okay, in this sort of plectic Selma group. Okay, so the question is, so inside here, of course, we have the wedge R of the rational points. Okay, so you may ask, well, do we actually get something non-zero which is in the wedge R of the rational points? In other words, can you write down an R tuple of rational points? Yeah, that would be higher rank. That would be, of course, great, wouldn't it? Okay, there are some problems there. First of all, you have to somehow relate the fact that this thing would end up inside this wedge R of the rational points with the fact that the L function vanishes toward R. That it does not seem so easy. Although, of course, there is an analogous work in the functional field case that you know about, where this is done, but that seems quite tricky. And then there's another problem. You might think, well, come on, I want to solve the BSD conjecture for elliptic curves over Q. So why don't I just base change to a field for which the order vanishing of the L function doesn't increase, okay? And then I do this construction here. But now the problem is that your base changing point, you've got your rational points mapped to elements of H1 of Q of T. So I mean, but they're p-adically linearly dependent because the QP points of E only have rank 1. So that way there's no hope of getting a non-zero element of this thing, locally anyway. So the usual method of analysis, which is considering this thing locally at P, is not going to work. Okay, so we thought about that quite a lot and realized there were lots of problems. But it's a very, of course, very interesting question.
Okay, I think we have no more time.
Thank you.